Dopamine was always known as the molecule of pleasure. But if that's true, why do we stop doing things that feel good? Why do we walk away from things that once made us happy? Because dopamine isn't what we think it is. Without it, we wouldn't give, we wouldn't take, and we would starve to death even with food in front of us. This is the molecule that drives the world, and the world would cease to exist if not for it, and life would have come to a standstill. This is a video about how this molecule was coincidentally discovered and how a series of neuroscientists and psychologists uncovered the actual truth through experiments that wiped out dopamine, and finally, how our minds exploit us. In 1954 at McGill University, psychologist James Olds and neuroscientist Peter Milner stumbled upon something extraordinary. A circuit in the brain that made rats seek stimulation over and over again. They found that some regions in the brain triggered responses associated with rewards, whereas other regions caused the animals to behave as if they were experiencing punishment. To understand this, they set up a Skinner box, where a simple switch was connected to a 60-cycle power source delivering between 0 and 10 volts through a stimulating electrode implanted in the brain. And that revealed stimulation in certain forebrain regions led to intense, repetitive lever pressing, a clear sign of reward. But in parts of the midbrain, the response was the opposite. The rats avoided the lever as if the stimulation felt like punishment. This was the first concrete evidence of a reward system in the brain. A circuit, when activated, drives an animal to repeat a behavior over and over. But there was still one unanswered question. What exactly was driving this reward system? What was the messenger molecule that told the brain, "This feels good, do it again"? And at that time, no one knew. The circuitry had been found, but the chemical was still a mystery. In the late 1950s, a drug called reserpine was being studied at the National Heart Institute in Sweden. It was used for treating high blood pressure and psychosis, but something strange was happening alongside. Animals given reserpine became still, quiet, and almost frozen. Bernard Brody and his team noticed that reserpine seemed to wipe out serotonin in the brain, a chemical responsible for mood, appetite, sleep, and cognition. But no one had ideas about other brain chemicals until a young neuropharmacologist from Sweden, Arvid Carlsson, joined the lab. Carlsson suspected that serotonin wasn't the whole story. He had a hunch that reserpine might also affect another group of molecules called catecholamines, which are dopamine, norepinephrine, and epinephrine, given its structural similarity to serotonin. His mentor Brody wasn't convinced, and Carlsson brought in his colleague Niels Hillap, a specialist in catecholamines, to test the idea. When they gave rabbits reserpine, the catecholamine levels in the adrenal gland, the heart, and most importantly in the brain dropped significantly, and the animals barely moved. It was as if their will to act had been shut off, and they reversed this frozen state with L-Dopa, a chemical precursor in catecholamine synthesis, and almost instantly the movement returned. Everything seemed to be fine, but when they analyzed the brain tissue, something didn't add up. They were expecting to find norepinephrine, the popularly known neurotransmitter at that time, and it wasn't found. So the next best solution would be to look for other molecules in the synthesis pathway. Catecholamines are made in steps, starting from an essential amino acid called phenylalanine, which comes from food. It is converted into tyrosine and then into L-Dopa and finally into dopamine, which gets converted into norepinephrine and epinephrine. The team had given the animals L-Dopa, expecting it to restore norepinephrine, but what they found instead was an increase in dopamine, and that changed everything. Dopamine, once thought to be just a chemical middleman, was doing something on its own. It was the molecule restoring movement. And Carlsson revealed the first known function of dopamine in the brain as a messenger molecule, and he called it a Rosetta Stone, the key to decoding the chemical language of the brain. For a time, that is all dopamine was believed to do, and further studies uncovered something more. That dopamine wasn't just a messenger molecule and it went beyond movement, and what it touched next would change everything known about behavior. Now that scientists had a clear picture of the brain's reward system and a working theory of a chemical messenger, labs across the world tried to answer a pressing question. Was dopamine responsible for reward-seeking behavior? And without a unifying study, it was difficult to draw a clear conclusion. That's when neuroscientist Roy Weiss stepped in. He analyzed the field as a whole, pulling together the fragmented research into a coherent story. His work laid the foundation for what would become one of the most influential ideas in modern neuroscience. Roy Weiss believed that the brain's reward system wasn't built for experiments or electrical pulses. He proposed that what Olds and Milner discovered wasn't artificial pleasure, but hijacking of the natural system. If all rewarding experiences from nourishment to affection to addiction trigger the same pursuit behavior, could they all be using the same neural pathway? And if so, was dopamine the common output? At the time, the answer was unclear. For nearly 15 years, the role of dopamine in reward went unanswered. Many scientists believe that norepinephrine or other catecholamines might be responsible. Weiss stimulated norepinephrine neurons using both electricity and targeted chemicals, expecting to see the same reinforcement response. But there was none. The animals didn't learn, they didn't repeat the behavior. Norepinephrine wasn't producing reward, it was dopamine that continued to stand out. And yet, there was another problem. Electrical stimulation, as used in Olds and Milner experiment, wasn't always clean. Electrodes could activate neighboring fiber neurons, and that meant that the early studies might have stimulated more than just the reward circuit. So Weiss turned to a different method, self-administration. He gave animals access to amphetamines which directly stimulate dopamine release, and what he observed was remarkable. Even when the drug was diluted, the animals would adjust how much they took, pressing the lever just enough to reach the level that felt right. The behavior was precisely calculated as if the animal could sense when their dopamine levels were just right. There was one last test to confirm if all these were indeed accurate. Weiss used dopamine blockers to shut the system down. The animals still had access to the drug, but their behavior changed. They pressed the lever less and less until they stopped altogether. He called this an extinction-like behavior. The desire to act had faded even though nothing in the environment had changed. The action had lost its meaning. Through these experiments, he showed something profound, that dopamine was not just a part of the reward system. It was important in how we perceived rewards and how behaviors were sustained. But for Weiss, this wasn't just about proving dopamine's involvement. He wanted dopamine research to be driven by a clear hypothesis, and that call led to one of the most profound studies in the history of neuroscience, which revealed that dopamine isn't just about reward, but it's about expectations. Have you noticed that it's the anticipation of a moment that excites you more than the moment itself? The wait before the package arrives and the moment just before you taste your favorite food. It's often not the reward that moves us, it's the urge leading up to it. If dopamine is thought to be a chemical of pleasure triggered by rewards, then what is it that drives this anticipation? Neuroscientist Wolfram Schultz ran a series of experiments with macaque monkeys, carefully recording the activity of dopamine neurons during the moments that led to a reward. He wasn't just interested in what happened after the monkeys received a reward. He wanted to know what happened before. He introduced an idea called prediction. A prediction, as he wrote, is an information about what's coming, a signal that lets the brain prepare for a future event based on what it has learned. But the association between reward and prediction wasn't new. It had been demonstrated nearly a century earlier in one of the most famous experiments in behavioral science. When Russian physiologist Ivan Pavlov was studying digestion in dogs, he noticed something strange. His dog began to salivate at the sight of the lab assistant who usually brought the food. The animal had learned to associate the cue with the reward, and over time, the cue became just as motivationally powerful as the reward itself. What Pavlov had found and what Schultz later confirmed at the level of neurons was that the brain doesn't wait for the reward. It learns the signal and prepares for what's coming. Schultz's recordings show that dopamine neurons spike not at the moment of reward, but at the moment of the stimulus that predicts the reward. And then something remarkable happens. If the reward arrives as predicted, there is no change. The brain was expecting it and nothing new was learned. But if the reward does not come, the dopamine activity drops. And that dip is what Schultz called a negative prediction error. The brain expecting something and reality disappointing it. The neurons use prediction error, and that's how we learn. What if the brain needs these errors? And what if these are not just learning signals but cravings? And the best dopamine spikes, they do not come from certainty but from uncertainty. Why do slot machines hook people more than vending machines? Why does a suspenseful movie light up your brain? It's because your brain does not just seek rewards. It gets excited by uncertainty and novelty. Schultz and his team discovered that when a reward is delivered at a predictable time, dopamine neurons begin to quiet down. The brain learns the pattern and the reward loses its novelty. But when the timing shifts, when a reward arrives sooner or later than expected, dopamine spikes again, often stronger and lasts longer. And once the new timing becomes predictable, dopamine quiets again. This reveals something powerful. The brain isn't just tracking rewards, it's tracking change. These subtle subconscious adjustments where dopamine neuron gradually decays dopamine levels based on input matches expectations to reality. And in simple terms, it's constantly learning. The concept of learning has fascinated scientists for centuries, long before Schultz recorded his first dopamine spike. How does a brain know when to strengthen an association and when to let it fade? It all came down to just one equation, called the Rescorla-Wagner model. The equation is a mathematical way of saying the strength of learning depends on three things: how noticeable a cue is, how powerful the reward is, and how unexpected the outcome is, which is the difference between what the brain thought would happen and what actually did. In other words, delta V is the product of salience, surprise, and reward strength. The dopamine neurons that Schultz studied followed the same pattern as the Rescorla-Wagner model, but there was one piece missing, something essential to how we learn in the real world. The Rescorla-Wagner model explained how we learn from prediction error, but it did not capture when these errors occurred. It had no sense of timing, no way to represent the delay between a cue and a reward. But in real life, outcomes don't always arrive instantly. It is always timed. Temporal difference learning is the brain's way of learning from what happens and when it happens. It doesn't just wait for the reward to show up to learn. Instead, it makes predictions at every step, updating them in real time as each moment passes. And this learning insight not only changed neuroscience, but it also reshaped artificial intelligence. Most of our motivated actions are learned responses, and for a long time, that was thought to mean we chase things that bring us joy. But here's the question: do we always chase things that bring us joy? And if not, why do we chase it? Around the 1990s, psychologist Ken C. Berridge made a discovery that would challenge everything the field thought it knew about dopamine and the brain's reward system. At the time, dopamine was thought to play one of three possible roles in reward. It might be the chemical of pleasure, it might be involved in reward learning, or it might be the driver of motivation. But these three ideas were often lumped together with little effort to tell them apart. Berridge designed a very specific experiment to test them. Using a neurotoxin called 6-hydroxydopamine, he wiped out nearly all the dopamine in the brains of rats. These dopamine-depleted rats became profoundly inert. They didn't explore, eat, or drink on their own. That part wasn't surprising. It had been seen before. But Berridge asked a deeper question. What exactly had been lost? Pleasure, learning, or motivation? If dopamine is the brain's pleasure chemical, then these rats should no longer experience pleasure, even when given something sweet. So he manually gave them drops of sugary liquid. And to his surprise, the rats still responded with the same positive facial reactions as the normal rats. And this disproved the idea that dopamine was necessary for pleasure. Then came the second test of learning. If dopamine is required for forming reward-related memories, these rats should fail to learn new associations. But even without dopamine, they still learn to avoid bitter taste, shown through aversive facial expressions. The only thing that was missing was motivation. These rats liked the reward and also learnt about them, but they no longer worked to get them. And that became the turning point. Dopamine was not the source of pleasure, it was a spark of pursuit. It didn't make things feel good, it made it feel important. And that's why it's often said a rat without dopamine would starve to death even with food in front of it. Berridge called this process incentive salience, the transformation of a neutral stimulus into something desirable, attractive, and compelling. A cue that now grabs our attention, a taste that now feels worth chasing, even if we no longer enjoy it. It wasn't just about motivation, it was also about timing. Does the brain want something right now, or can it hold back and wait for the right moment? This turns out to be one of the most important ways dopamine shapes our behavior, especially in humans with a highly developed prefrontal cortex, the part of the brain that decides whether the reward system gets what it wants or has to wait. Imagine this: you're offered a choice. You can either have one marshmallow right now or two marshmallows if you wait 10 minutes. What would you do? Now imagine the same choice, but this time you're a 4-year-old. How different would your decision be? A child still developing impulse control versus an adult with a fully developed prefrontal cortex, capable of managing desire and waiting for the bigger reward. This is exactly what psychologist Walter Mischel set out to study, a famous test in psychology known as the marshmallow test. But over time, these experiments showed something deeper, that even though our choices may look different across situations, we make our everyday choices in a similar way without realizing the process behind it. The study focused on three powerful variables: time to reward, attention to reward, and the distractions that resist temptation. Michel observed that when given a choice and predicted outcome, the ability to wait was influenced by several key factors. First, the perceived value of the reward. The greater the payoff, the longer the delay. And when children truly believed that the reward would come, they waited longer. Second, their age and maturity. Older children with more developed control were more likely to delay gratification. And third, something more subtle: social influence. The decision was often shaped by what others did. Sigmund Freud, the neurologist who laid the foundation for psychoanalysis, proposed that people are able to delay gratification by forming mental representations of the rewards they desire. Michel's experiments revealed something surprising. Children who kept their eyes on the marshmallow were far more likely to give in early. The ones who succeeded, they distracted themselves with imagination, conversations, and daydreams. Some turned away, some closed their eyes, and a few even fell asleep. And then came another twist. When the reward was covered up, hidden from sight, children waited even longer. So if attention makes it harder and distraction isn't always enough, is there a way to look at the reward without wanting it? Michel found out that there was a specific kind of attention that did not resist the marshmallow but reframed it. In one variation of the experiment, children were shown life-size images of the marshmallow instead of the real thing. Surprisingly, they were able to wait 3 times longer for an average of 18 minutes compared to just 6 minutes when the real marshmallow was placed right in front of them. This reveals something profound. There are two ways the brain can represent a reward. One is consummatory, that is emotionally arousing. The other is abstract or non-consummatory, and only one of them helps us wait. When the brain views the reward as something consumable, delay becomes far more difficult. But when the reward is framed in a non-consumable, abstract way, even just mentally, the ability to wait increases dramatically. But even with that ability, age, and brain maturity, delaying gratification is also shaped by environment and context. And that's why Michel wrote, "To wait isn't just about patience, it's about freedom, the power to choose long-term meaning over short-term impulse. And without that, there is no real choice at all." But the reward system isn't foolproof. What if it started treating an unnatural stimulus as more valuable? And what if the brain kept chasing it over and over again, even when it no longer brought any real pleasure? Hijack slowly and quietly until the moment you realize it's no longer in your control. Dopamine isn't just a chemical messenger, it is a compass, a chemical whisper that nudges us forward, sometimes towards our goals and sometimes towards our destruction. For years, we thought dopamine was all about pleasure, but it is not. It is about the pursuit, the urge, craving, and the pull to act. And now that we understand it, even a little, maybe we can choose where we let it lead us.